In this video, we're discussing learning outcome number 2, which is about 4 common approaches to estimating probabilities or finding probabilities of some event happening. And then we're going to interpret the relative frequency approximations that we'll discuss as measures of probability using the law of large numbers. Every time I think of probability, I think of this scene from this movie, so I'm going to share it with you. This is from Dumb and Dumber. I may be dating myself here.
What are my chances?
Not good.
You mean not good like 1 out of 100?
I'd say more like 1 out of 1 million.
So you're telling me there's a chance? Yeah!
It's hilarious. Okay, that's all I wanted to show you from that. You get the idea. Probabilities, they are measures of likelihood, whether or not there is a chance. So that is a great segue into interpreting probabilities, which we're going to talk about in just a moment. But let's start by looking at some notation for probabilities. So P denotes a probability, and usually we say P of something. That something is denoting a specific event. So we're going to use capital letters A, B, and C typically to denote specific events. And so when you see this, you want to think of it like function notation. That's not multiplication, that's like function notation. This is like the probability of A occurring. Now sometimes rather than listing A as some event and then writing the probability of A using this notation, people will just write out the event A in words. So let's say you're talking about rolling a die and A is the event of rolling an even number. Rather than writing A equals rolling an even number and probability of A equals using this notation, people will often write P of rolling an even number, and they will literally write rolling an even number in those parentheses. That is a fine notation, but this is the notation using these capital letters. This is more common when you look at the literature and when you look at your textbook, but in more informal textbooks, including our own, they will often, instead of writing A, will write probability of whatever it is, that event that you're looking at. Like, what's the probability of rolling an even number? What is the probability of rolling a 5? Probability of choosing a queen from a deck of cards or something like that. So that's our notation. And then this slide is all about interpreting those probabilities. And this is where I think of Lloyd and Mary from Dumb and Dumber a lot. And I definitely think I am dating myself with that movie reference, but it's great. It's a great example of a probability that is very unlikely. So probabilities are measures of likelihood. They are a way that we can talk about how likely it is that something is going to happen. Now, I tend to think of probabilities in terms of percentages, but whenever we look at probabilities in the literature, in our book, anywhere, they're typically represented by proportions. So they're represented by fractions or decimals, and those fractions or decimals are proportions between 0 and 1. But if you multiply those proportions by 100%, then you can think of them in terms of percent chance that something is likely to happen. And that is how I interpret it. Now again, probabilities aren't represented by percentages. They're typically represented by these numbers between 0 and 1 instead. But I think translating to percentages really helped me to understand what a probability is. So let's go through some common expressions of likelihood and the corresponding probability. So if you have an event that's absolutely impossible, then it has a probability of 0 or a 0 probability. I think Mary could have said to Lloyd that the probability of dating her was 0, but she was much kinder than that. Instead, she said the probability of them getting together was 1 in a million. So when she said it was 1 in a million, She was saying there was a chance, just like Lloyd mentioned, but she was also saying it was very unlikely. Now, if something is completely impossible, it is not going to happen. There is zero probability of that event happening. Or we would say there's a 0% chance of that happening. Now, if you're certain that something is going to happen, if you have a certain event, there's a 100% chance of that happening. Now, that 100% corresponds to a probability of 1. So if something is certain, it has a probability of 1. Now, if something is very, very likely, but not certain, if, for example, it's very, very likely that the sun is going to come up tomorrow morning, but we can't be certain that the sun is going to come up tomorrow morning, then that probability would be very close to 1, but it wouldn't actually be 1. Maybe it's 0.99999, and there's a lot of nines because it is very, very likely that the sun is going to come up tomorrow morning, but there's a very tiny chance that it might not. So those are certain events. Now, if we ever say that there's a 50-50 chance of something happening, that's a 50% chance of it happening and a 50% chance of it not happening. A 50% chance corresponds to a probability of 0.5. So events that are very unlikely are small positive numbers. They're just a little bit more than 0. Events that are impossible have a probability of 0. Events that are certain to happen have a probability of 1. And events that are very likely to happen have a probability near 1. And then, of course, we could have any probability in between. So, for example, when you talk about a 30% chance of rain tomorrow, well, they're saying that there's a 30% chance that it's actually going to rain and a 70% chance that it's not. That 30% chance of rain would correspond to a probability of 0.30. You would just move that decimal twice in order to get the probability. Now, this is the core of how we're going to interpret probabilities in our course. Probabilities always have to be between 0 and 1, and they have these types of interpretations. You can never have a negative probability because there's never a negative % chance of something happening. So it doesn't make sense to talk about negative probabilities. It also doesn't make sense to talk about probabilities that are greater than 1. The example I always think of, and this is not with regard to probability, but just with regard to proportions, is this idea that people are supposed to give 110%. There's one of my favorite professors at the University of Tulsa, and he used to say that a person cannot give 110%. And he was very adamant. He was like, they are only one person. They are not 1.1 person. Since they are not 1.1 person, they cannot give 110%. In much the same way, we can't have a probability of 110%. It is either certain to happen or not certain to happen. But at any level of certainty, it's between 0 and 1. It's never 110% likely to happen, if that makes sense. And if it's not 110% likely to happen, that means a probability of 1.1 doesn't make any sense. So if you have probabilities that are listed, or if you have numbers that are greater than 1, strictly greater than 1, those can't represent probabilities. If you have numbers that are less than 0, so they're negative, they can't represent probabilities. But all of the numbers between 0 and 1, those numbers represent a measure of the likelihood that some event is going to happen. And those all make sense. If it's a small positive number, it's unlikely. If it's a larger number, a little bit less than 1, it's very likely. And then we've got the range of possibilities in between. Now, I've said right here that impossible events have a 0 probability. So if that event is not going to happen, its probability is 0. The probability of that impossible event happening is 0. But I didn't say that if an event has 0 probability, it's impossible. So that doesn't actually go the other way. Just because an event has a 0 probability does not necessarily mean that that event is impossible. Now, there's an excellent video about this by Grant Sanderson of 3 Blue, 1 Brown. I'm going to put that on our YouTube playlist for statistics, and it'll also be posted on our Blackboard site. But again, we're typically focused on the interpretations on this bar graph on the right-hand side or on this list right here. If something is impossible, it has a 0 probability. If something is certain to happen, it has a probability of 1. And then if it is likely or unlikely or has some probability in between, you're going to see a probability between 0 and 1. But 0 probabilities don't mean the events are impossible. And if you're curious about that, you'll have to watch Grant's video. It's fantastic. Now we're going to talk about finding probabilities or estimating probabilities using 4 methods, and I will list them for you here. So here's our first method. It's called a relative frequency approximation. This is an approximation of probability that we calculate by doing the following. We're going to conduct a procedure or observe a procedure being done a number of times. And then we count the number of times that the event A that we're interested in occurs. Then the probability of event A occurring is approximately equal to the number of times it occurred divided by the number of times that a procedure was run. So this is based on data collected in the past, and it gives us an approximation of that probability. And it's an approximation that is trustworthy based on the law of large numbers, which we'll talk about in just a moment. Now, there's also the classical approach to probability. This is not dealing with events that have happened. This is dealing with events that can happen and the possible events that can happen. So with the classical approach, we'll say this: if an event A can occur in S different ways, and a procedure has N different simple events that are equally likely, so they have to be equally likely. And when we say N different simple events that are equally likely, we're usually talking about those N events in the sample space. So you find the sample space first, you find all the possibilities that are simple, and then you say, if event A can occur in S of those ways, then you just take the number of ways A can occur divided by the number of outcomes that are possible, and that is equal to the classical probability of the event A occurring. Now, we also have subjective probabilities. These are just estimates that people make based on their usually intuitive understanding of relevant factors. So, for example, when Mary was saying there's a 1 in a million chance that she would go out with Lloyd, that was a subjective probability. She was basing that on the fact that she was married and probably not interested in Lloyd. But that was a subjective probability because it was a personal estimate based on her understanding of herself and Lloyd and the situation. And then lastly, we have simulations that allow us to estimate or find probabilities. And in a simulation, basically we're doing the same thing that we do with a relative frequency approximation. It's just a little bit different. With that relative frequency approximation, we're conducting or observing a procedure as it actually happened, and then counting the number of times that the event A actually happened. In a simulation, we're not actually watching it happen, but we're simulating it. We're acting as if it happened. We're saying, okay, if it did happen, what would that look like? And let's conduct that simulation of the procedure, and then let's conduct that simulation of the procedure again, and let's do it a number of times. And then we look at that simulation and all of the outcomes of the simulation, and then we count the number of times that event A occurred in the simulated repetition of the experiment of the procedure. So a simulation is giving you data that is very similar to what you get from that relative frequency approximation. But in the simulation, it actually hasn't occurred. We've just pretended like it did occur and then counted the number of ways or times that event A occurred in the simulation. So now we're going to go through these one by one and look at some examples. So with our relative frequency approximation of probability, we conduct or observe a procedure and then count the number of times that event A occurs. Then the probability can be approximated in the following way. This is not an exact probability. but it's an approximation of the probability, and it's given by this formula. The probability that event A occurs is approximately equal to the number of times that event A occurred divided by the number of times that procedure was repeated. We're going to talk about that more when we talk about the law of large numbers in just a moment. So here's an example where it's dealing with deaths in skydiving accidents. It says, in a recent year, there were about 3 million skydiving jumps, and 21 of them resulted in deaths. The question says, find the probability of dying when making a skydiving jump, or alternatively, approximate the probability of dying when making a skydiving jump. Well, we can approximate that probability using this formula. Now, this is what I was talking about before. Rather than saying A is equal to death during a skydiving accident, sometimes it's denoted this way. The probability of a skydiving death is this. It's the number of skydiving deaths, approximately, over the number of skydiving jumps. So how many jumps were there total? How many of those were deaths? Well, there were 21 deaths out of 3 million times that this procedure was run. And so the probability turns out to be 0.000007. So that's the probability of a skydiving death approximately based on this data from the past, where 21 people out of the 3 million skydivers passed away in an accident. So we've got this measure of probability, but again, it's an approximation because it's not taking into account like the number of skydiving deaths that can occur out of all the number of possible jumps. It's a little different than that classical approach. So, and I think it makes sense to use the relative frequency approach here because of the nature of the data and the nature of our understanding of these variables. So we just take the number of deaths and we divide by the number of jumps and we get this probability. And it's an estimate of the probability of dying during a skydiving accident. Now in our second approach, this is called the classical approach to probability. You're going to see a fraction that looks very similar, but this is a little bit different than that relative frequency approximation. This is dealing with the case that you have a procedure and there are n different simple events that are equally likely as possible outcomes. So you know what that procedure is, you find the sample space, and then you look at the sample space and it consists of n different simple events. If all of those are equally likely, and event A can occur in S of those n ways, then the probability is the number of ways that A can occur divided by the number of possible things that could happen. So we've got the number of ways that A can happen divided by the number of things that could happen, and that is the definition of the classical probability of the event A occurring. So notice that this is similar to what we looked at on the last slide with that relative frequency approximation. But know that with the relative frequency approximation, we're looking at data from the past. With the classical approach, we're looking at probability of an event that has not yet occurred. We're thinking about probabilities that this is the number of ways that A can occur out of the number of things that could happen, as opposed to the number of times that A did occur out of the number of times that the procedure was run, which was like the relative frequency approach that we were looking at. But it seems very similar. It's dealing with the number of ways A can occur divided by the total number of possible outcomes, provided that all of those outcomes are equally likely. Now, you always have to confirm that those outcomes are equally likely. If they're not equally likely, then this is not the way to compute the appropriate probability. So here is an example where we're asked to use the classical approach. The question asks us to find the probability of rolling an odd number when rolling a traditional 6-sided die. So you think, okay, well, what's the sample space? That's the first thing. Well, if you roll a die and you roll it once, you can get a 1, a 2, a 3, a 4, a 5, or a 6. And then the question says, what is the probability of rolling an odd number? Well, how many ways can you roll an odd number from the sample space? Well, if you rolled a 1, that would be an odd number. If you rolled a 3, that would be an odd number. If you rolled a 5, that would be an odd number. So there are 3 ways that you can roll an odd number out of the 6 possible outcomes. So the probability of rolling an odd number is 3 out of 6, which simplifies to 1/2 or 0.5. So there's a 50% chance, if you prefer, of rolling an odd number, but we won't call it a 50% chance. Instead, we'll call it a probability of 0.5. Now, let's look at that skydiving example again. It says, in a recent year, there were about 3 million skydiving jumps and 21 of them resulted in deaths. Find or approximate the probability of dying when making a jump. Is it appropriate to use the classical approach here? That's the question. Say, well, what are the possible outcomes? The possible outcomes are death and not death, death and survival. Would it make sense to use the classical approach here? We'll say no, it absolutely should not be used here. We will talk about binomial distributions later in this course, and that would be relevant here. But when we're talking about whether you live or die after a skydive, we should not use that classical approach, because dying and surviving, the 2 possible outcomes, are not equally likely. And of course, that probability of dying or surviving depends a lot on your training and your background. If you are well trained, and there are other things that come into account too, the weather, things like that, those affect the probability of dying and the probability of survival. So they should certainly be taken into account when we calculate probabilities. So we can't use the classical approach here. You don't have a 1 in 2 chance of dying, because you've got one outcome of dying, 1 outcome of surviving. So there's 2 outcomes. So that's the chance of dying. That's 1 out of 2. You don't want to do that here, because there's much more that goes into whether or not you die or survive than just random chance of picking one of those 2 categories. These are not equally likely outcomes, so we should not use the classical approach here. And the law of large numbers is related to both of these approaches that we just discussed, but it's particularly relevant to that relative frequency approach. This says that as a procedure is repeated, the relative probability of an event tends to approach the actual probability. And when we say actual probability, what we're talking about is that classical probability, the classical probability that we would find when we consider the number of ways something can occur out of the number of possible things that could occur. So if we repeat a procedure a number of times, it turns out that that relative frequency probability will approach the actual probability. I think the easiest way to think of this is in terms of flipping a coin. If you think of this in a classical sense, if you're flipping a coin, you have a 1 in 2 chance of flipping and then getting a heads, right? But if you flip a coin 5 times, are you guaranteed to get 2.5 heads? Well, no. You might get heads 5 times, you might get tails 5 times, you might get heads 1 time and then tails 4 times. Who knows? But each time you flip the coin, you've got a 1 in 2 chance, provided it's a fair coin. And that's dealing with the actual probability. But if I flipped a coin 100 times, or 1,000 times, or 1,000,000 times, that relative frequency probability would tend to approach the actual probability. So if I flip the coin 1,000,000 times, I would expect that if I looked at all of that data, about half the time I would get heads if it was a fair coin. So about half the time, half of 1,000,000 out of a million would give me 1/2, which is approaching the actual probability. But if I flip the coin twice and I get tails twice, does that mean there's a 0 probability of getting heads? Absolutely not. It just means due to chance, you got 0 when you flip the coin twice. But as we flip the coin more and more and more and more times, and as we look at the data that summarizes all of those trials all at the same time, which would be given by that relative frequency probability, the number of times we got heads out of the number of times we flipped the coin. That number of times we got heads out of the number of times we flipped a coin would tend to approach that actual classical probability of 1/2 as we repeat that procedure a number of times. This is called the law of large numbers because it says if you keep doing it, if your sample size is large enough, that relative frequency probability is going to tend to approach the actual probability. So when we look at that skydiving data, since there were 3 million skydives that year, 3 million, I'd say that the sample size is large enough that that relative frequency approximation of probability is probably pretty close to the actual probability of dying during a skydiving jump, at least within a year or two, as long as other factors don't change. Now you have to be really careful about the law of large numbers. A lot of people make the mistake of misinterpreting this. This is dealing with behavior over a large number of trials. So this is dealing with that fraction, the number of times that something occurred out of the number of times we tried, out of the number of attempts that we made. If we're looking at that fraction over a really long time, over a large number of trials, as that denominator gets larger and larger, the fraction is going to approach the actual classical probability. This does not say anything about the next trial. Does that make sense? It does not say anything about what's going to happen the next time I flip that coin. So if you are flipping a coin and flipping a coin and flipping a coin, and every time you get heads, that's a win for you. And if you got 5 heads in a row, you might think to yourself, I'm due for a tails. People make this mistake if they go to the casino sometimes. If they're on a winning streak, they might think, oh, well, this machine is maybe due to not win the next time. Or if they're on a losing streak, they might think, I'm due to win the next time because I lost so many times in a row. All of those previous losses or previous wins and all of the previous trials have almost nothing to do, typically, with the next trial. So if you flip that coin one more time, you still have a 50% chance of getting heads, a 50% chance of getting tails, or a probability of 1/2 of getting heads and a probability of 1/2 of getting tails. And all of the other trials that happened before it have absolutely nothing to do with what's going to happen next. But if we looked at the number of times you got heads over many trials, and you looked at that fraction would tend to approach the actual classical probability. Now, when dealing with classical probability, this is really important. If you know nothing about the likelihood of the possible outcomes, it's never appropriate to assume that those outcomes are equally likely. So if you're talking about dying in a skydiving accident, and the 2 outcomes are survival and death, we should never, assume that survival and death are equally likely. It's not a 1 in 2 chance that you survive or a 1 in 2 chance that you die. I also think of this in terms of divorce. People sometimes will say, oh, you have a 50-50 shot of staying married. And sometimes that might be relevant depending on the statistics that you're looking at with divorce rates and things like that. But if they're saying that there's a 50-50 chance of staying married because they're saying you either stay married or you don't. There's a 50% chance of staying married because 1 in 2 chance of staying married, and then there's a 1 in 2 chance of not staying married. I don't think that that's accurate at all. So you got to be careful. If the events are not necessarily equally likely, you shouldn't treat them as if they were equally likely. So another example that's similar to that is passing or failing your upcoming statistics exam. You don't have a 50-50 shot of passing or failing. It's not, oh, I might pass or I might fail, and those are the options. What other considerations should you keep in mind? Well, maybe studying, how much you prepared, how difficult the test was, or how difficult the test is, how clear the instructions were, how clear the preparation instructions were. All of those things may affect your ability to pass or fail an exam, or your concentration, or things that are going on in your life or in your environment, the amount of time that you were able to devote to studying. All of that may influence whether or not you pass or fail an exam. So you don't have a 1 in 2 chance of passing and a 1 in 2 chance of failing. The passing and failing also depend on other factors. So we should not assume that the outcomes are equally likely, which means we should not use a classical approach here. Now, the third approach is that subjective probability. That's a probability being estimated using knowledge of relevant circumstances. This is typically done by individuals. When you say, what's the chance that you got an A on that test? And you say, oh, I feel like I'm 80% sure I got an A. Have you ever had that conversation with a friend? I'm about this percent sure that this is going to happen. That's a subjective probability. That person is pulling a number out of the air, but it's pulling a number out of the air based on intuition and based on intuition based on relevant circumstances. So when Mary said, there's a 1 in a million chance that we could go out, she was using a subjective probability. Now, simulations, as I mentioned before, are a process that behaves in the same way or same ways as the procedure itself so that similar results are produced. So this is where you're not actually seeing something happen, but you are simulating that something happening. And as you simulate that thing happening over and over again, you can count the number of times that the event A that you were interested in occurred in the simulation. And then you can calculate something that's very similar to that relative frequency approximation. So you can find out how many times that the event occurred in the simulation, and you can divide by the number of times that that procedure was simulated. And that's going to give you an approximation of probability, provided that your simulation is simulating what it's intending to simulate in a relatively accurate way. And I'm using a lot of qualifiers, and we can say, well, what do you mean by relatively accurate? All of it is intentionally vague because these things are difficult to measure. Okay, now, when we're calculating probabilities, there are some rounding conventions, and these are the rounding conventions that Mr. Triola, the author of our textbook, tends to use. When we're expressing a value of a probability, we often like to give the exact fraction or decimal when we can. If it's a fraction, that means that we can write it as a terminating decimal. And sometimes we will write it as that terminating decimal because it helps us to see that percentage likelihood that I always tend to convert to. It gives me a better sense of what the number is when I see it in the form of a decimal, as opposed to saying, you have a 31 out of 68 chance. Say, oh, well, that's kind of close to 50% because 31 is close to 30 and 68 is close to 60 maybe. But if you convert it to a decimal, you'd have a much better understanding of what percent that was. So you could use your calculator to simplify a fraction and leave it as an exact fraction, or use a calculator to get a terminating decimal that is equal to that exact fraction. Now, if you have decimal results that maybe are very long, we tend to round to 3 significant digits. And if you want, we can talk more about significant digits. That's really a prerequisite for our course, but let me know if you need some help with significant digits and we can go over that. And so here's a suggestion. If you're dealing with a fraction that's not simple, like 2 out of 3 or 5 out of 9, sometimes it's helpful to express it as a decimal so that the number can be better understood. Now, in this last example, I'm going to show you a potential pitfall when it comes to computing probabilities. A lot of students make this mistake. So here's a problem statement, and then we'll try to solve it. The question says, in a study of US high school drivers, it was found that 3,785 texted while driving during the previous 30 days, and 4,720 did not text while driving during the same time period. Based on these results, if a high school driver is randomly selected, approximate the probability that he or she texted while driving during the past 30 days. Now, here's the mistake, the common error that many students make. They think, probability. I'm just going to take the small number, I'm going to divide by the large number. Don't do it. Do not do it. People just often, when they see problem statements in a math class, they just see numbers. If they know that they're supposed to divide things, they start dividing things. And if they're thinking about probabilities, they might do the 3,785 divided by that 4,720. Don't do it. Instead, I want you to think about what this problem statement says. First, we're going to write down anything that's given. And then we're also going to write down anything relevant that can be inferred from what is given. So what do we know? We know that there are 3,785 students that texted while driving. And then there were 4,720 students that did not text while driving. So we should write that down. Now, if you're talking about the total number of students in the study, the total number of students that we have data for, you have to add those two numbers together. So the total number of drivers in our sample was 8,505. Now, when you're asked what is the probability that somebody texted while driving, you're going to take this number that texted while driving, and you'll divide by the number of drivers in the sample. That's the same as the number of times that procedure was run. Now, this is another relative frequency approximation because we're using past data, and we're seeing the number of times that somebody texted while driving out of the total number of drivers that we were interested in. But you gotta be really careful. Don't just divide the 3,785 by this. Make sure you know what you're looking at first. So we're using that relative frequency approach. We take the number who texted while driving, we divide by the number of drivers in the sample. So that's the number of times that that procedure was run, and we get this 0.445 as a decimal approximation of the probability that a student would text while driving. So the data suggests that there is a probability of 0.445 that if a high school driver is randomly selected, he or she texted while driving during the past 30 days, excuse me. So the data suggests this. So this is an approximation of probability. It's not a guarantee, but if we took larger sample sizes, in theory, due to the law of large numbers, we would expect this to target and get close to the true probability that a student would text while driving for a given student on a given trial, and just one particular kid. Now, if I'm interpreting this 0.445, I can think of that as a 44.5% chance that if the high school driver is randomly selected, he or she texted while driving during the past 30 days. But a lot of people say you should never use probabilities or percentages when it comes to probabilities. I still prefer to use percentages to help me interpret what a probability means. But then remember, you gotta move that decimal over twice in order to get the true probability, which is a proportion. It's a number between 0 and 1. So that's the end of this lesson and learning outcome, excuse me. I'll see you for the next learning outcome.